So today we're going to look at particle motion some more, and let's just jump into some problems and show how you work them out, okay? So this first example, particle moves along the x-axis with velocity given by v of t, all right? For time t is greater than or equal to 0. If the particle is at position x equals -9 at time t equals 3, what is the position of the particle at time t equals 2? So because we have the velocity function, we can integrate that, and the antiderivative of velocity is going to be position. And when we integrate a definite integral, okay, we have to evaluate the antiderivatives at the lower limit and the upper limit. So that's how we're going to go about finding this, okay? So right here, what this is telling us at t equals 3, x equals -9, that means that x of 3 would equal -9. And we want to know the position, so at t equals 2. So we want to find x of 2. All right. So that's the question. Like, how do we find that, right? Well, because we have two position, right? We're trying to find the position at 2, and when we have the position at 3, we can use an integral of the velocity to get that. All right. So what we're going to do is we're going to take the integral from 2 to 3 of v of t dt, and recall the antiderivative of v of t is going to be x of t. So this is going to be x of 3, because we put the upper limit in first, x of 3 minus x of 2. We know it's going to come out to be this. All right. Now, what we can do is we can move this over to the other side. We can write an equation actually to solve this already. So we can add x of 2 to both sides, and that would give us x of 2 plus the integral from 2 to 3 of v of t dt. That would give us x of 3. Okay. And then if I move this integral, that will be solving for x of 2, which is I'm trying to find, right? So x of 2 is equal to x of 3 minus the integral from 2 to 3 of v of t dt. All right. And so what is v of t? Well, v of t is this function 3t squared plus 3, which is going to be a pretty easy integral to take. All right. What I'm going to do next is I'm going to replace everything. Okay. So this is going to be x of 2. That's what we're actually trying to find. And I know x of 3 from up here, the x of 3 is equal to -9. And then we want to subtract this integral from 2 to 3 of v of t. Now I'm going to write in the function now, 3t squared plus 3. So 3t squared plus 3. And then we need to remember our dt here, okay? So the antiderivative of this, right, we got to find that. So x of 2 is equal to -9 minus, and then this integral is going to be 3t cubed over 3, which would give me just t cubed, and then plus 3t. And then we want to evaluate that between 2 and 3, okay? All right, so that means x of 2 is equal to -9 minus, okay, so my bracket, and then I'm going to evaluate this at 3. So that would be 3 cubed plus 3 times 3. And then minus putting 2 in. So this would be 2 cubed plus 3 times 2. And then close my bracket. All right, so then that's x of 2 is going to equal -9 minus, and 3 cubed, this would be 27 plus 9, and then that would give you 36. And then minus, and then 2 cubed is 8, and then 3 times 2 is 6. So this would be 8 plus 6, which is 14. So I'm going to subtract 14 from this. And that gives me x of 2 would equal -9 minus 22. Which gives me a position at time t equals 2 of -9 minus 22, which is actually -31. All right. And so there's my answer. That's where the position of the particle was at t equals 2. It was at -31. Okay. And so we can do this, you know, if this was acceleration, we could find a particular velocity, right? Because the antiderivative of acceleration is velocity. And we can do a lot of different things with this. All right. And just know that this isn't just simply velocity to position. We can do acceleration to velocity also. Okay. So for our second example, we have a particle that's going to move along the x-axis again. But it has acceleration given by a of t is equal to 3 pi sine of 3 pi t for time t greater than or equal to 0. And if the particle has velocity v is equal to -2 at time t equals 1/3, determine if the speed of the particle is increasing or decreasing at time t equals 1/2. All right. So what this is giving us right here is a velocity, like I just said in the previous example, right? So this is telling us right here, this part right here of the question is telling us v of 1/3 is equal to -2. And we want to figure out, okay, is the speed of the particle increasing or decreasing at time t equals 1/2? So we want to find something out about 1/2, right? And is it increasing? Well, speed increasing means speeding up. And decreasing means slowing down. So to know if a particle or something is speeding up or slowing down, you got to look at what is the value of the acceleration and the velocity, right? And we're trying to do this at 1/2. So we need to find a of 1/2, right? And we also need to find v of 1/2. And we're going to be able to get a of 1/2 because we're given the acceleration function, right? All right. So we want to find the acceleration at time 1/2. Okay, so that'd be 3 pi sine of 3 pi times t, right? And t is 1/2, so times 1/2. And so that gives us 3 pi sine of 3 pi over 2. Okay, so we need to evaluate sine of 3 pi over 2, right? Well, where is 3 pi over 2? Well, if you recall, it's the negative y-axis right here. Okay, so right there, our x is 0, our y is going to be -1, and our r is going to be 1. And the sine ratio is y over r, so this is going to be -1 over 1, which is going to be -1. So this gives us 3 pi times -1, or -3 pi. So at t equals 1/2, we know our acceleration is negative, right? Because we have a -3 pi. So we know it's negative. Now, depending on what the velocity is at 1/2, then we're going to be able to determine if it's either speeding up or slowing down, right? So now we got to think, okay, so how do I get the velocity at 1/2? The way we get the velocity at 1/2, if we have the acceleration function, we're going to need to integrate, all right? And since we're given 1/3, we can use that to get the value of the velocity at positive 1/2, okay? So what we're going to do is we're going to integrate. And very similar to what we did just in the last example, okay, but it's with velocity instead. And since 1/3 is smaller, I'm going to put that one on the lower limit, and 1/2 is larger, so I'm going to put that on the upper limit. And then this is going to be a of t dt. And then we know that that's going to come out to be, because the antiderivative of acceleration is velocity, this has to come out to be v of 1/2 minus v of 1/3. All right. And I know this v of 1/3, right? It's -2. Okay. All right. So, I mean, there's different ways we can do this. Okay. We can move the v of 1/2 over to the other side and do all that, right? But what ultimately happens is that we can add v of 1/3 to both sides, right? And then we're going to have v of 1/3 plus this integral 1/3 to 1/2 of a of t. And we know that's going to come out to be this thing that's remaining, v of 1/2. Okay, so v of 1/3, I know is -2. So I'm going to go ahead and rewrite this, evaluating this. So v of 1/2 is going to equal v of 1/3 and then plus this integral 1/3 to 1/2. And my a of t function, I'm going to go ahead and write it. So it's 3 pi sine of 3 pi t. And then dt. Okay, so v of 1/2 is equal to, so v of 1/3, v of 1/3 we got up here, it's -2. And then plus, okay. So for right here, what we're going to need to do to evaluate this, we're going to do a u substitution, okay? All right, and I'm going to let u equal 3 pi t. And I'm going to grab a different color for my u substitution. I'm going to use a different color. And so I'm going to use, if I could find the pin that works. Okay, we're going to use u is equal to 3 pi t, and then du is 3 pi, and then dt, right? So this 3 pi right here, along with the dt, makes up my du. So that's going to be a nice integral because it becomes sine of u, right? Now we're also going to need to change our lower limit and upper limit to u values, okay? So that makes, this is going to be, when I put this in here, 3 pi times 1/3, that would just be pi. When I put 1/2 in here, it's going to be 3 pi over 2. And this becomes sine of u and then du. And that makes it a much easier integral, okay? All right. So then that makes v of 1/2 equal to -2. And then plus, and the integral of sine of u is negative cosine of u. So I'm going to put that in bracket, negative cosine of u. And we're going to evaluate that between pi and 3 pi over 2. Okay, so that means v of 1/2 is equal to -2 plus, and it's going to be negative cosine of 3 pi over 2 minus this, right? So that's actually going to make it plus. So it's going to minus a negative cosine, right? So that's going to make it plus cosine of pi. Okay, so 3 pi over 2, we can come back up here and use this diagram again. So cosine, this is going to be 0. So v of 1/2 is equal to -2 plus 0 plus, and then cosine of pi. Okay, so cosine of pi. So where's angle pi? Angle pi is on the negative x-axis. And because it lands right there, my x, I'm going to make my x be -1, my y be 0, and my r is going to be 1, because that's the radius of this point. That's this, the radius of the circle that this point's going around. All right, so then cosine is x over r. So my x is -1 and my r is 1. So that makes this -1. So basically what we have is -2 plus -1, right? Which is -3. Okay, so what does that tell us? Okay, so from the very get-go, right, we figured out the acceleration was negative and also the velocity was negative, which tells us that this particle at time t equals 1/2, the speed of the particle is increasing, okay? Now on delta math, because you're going to have these on delta math, right? You're going to have to fill in a sentence frame, all right? So basically, we're going to need to do this, all right? So since velocity and acceleration, all right, I'm going to underline that. So since velocity and acceleration have the same sign, and that's going to be important that they have the same sign. That's telling us the particle speed. So we'll write the particle speed is, and what is it doing? Because the velocity and acceleration have the same sign, then that means is increasing, which also means speeding up. And we have to say, so it's not always doing this, it's just doing it at this time. And that's what it was asking you. Is it speed increasing or decreasing at t equals 1/2? So we need to include that in our sentence. So at t equals 1/2, all right? So, you're gonna have to put in whether increasing, decreasing, and then you're also gonna have to type in this, all right? So that's how you do a problem like this, okay? All right, we're gonna do a very similar problem next, okay? So for this next example, example 3, again, a particle is moving along the x-axis. We're given the velocity function 6 pi cosine of pi t for time t is greater than or equals 0. If the particle is at position x equals 2 at time t equals 1/6, determine if the particle is moving towards the origin or away from the origin at time t equals 5/6. So to know if a particle is moving towards the origin, towards 0, 0, or away from it, right? What we have to look at is, okay, what is the position at that moment in time at 5/6? What's the position? All right. And then also, what's the velocity? Are you on the left side or the right side? And then are you moving left or are you moving right? Because I'm saying left and right because we're on the x-axis. Okay. So that'd be left and right. So we got to look at a combination, just like we did with acceleration and velocity in the last example, but what we're going to have to look at is velocity and position. So if we're on the positive side and the velocity is positive, that means we're on the right side moving right. And that would mean, for instance, we're moving away from the origin, okay? Versus if we're on the right side moving left, that means we would be moving towards the origin. So we got to look at the combinations of both sign, or both velocity and position at this time to see if the particle is moving towards or away from the origin, okay? So if the particle is at position x equals 2 at 1/6, so that's a position, right? So that's telling us right there that x of 1/6 is equal to 2, all right? Determine if the particle is moving towards the origin or away from the origin at 5/6, right? So right off the get-go, let's find what is v of 5/6, right? Because if we can do that because we're given the velocity function, all we need to do is just plug it in, right? So this is 6 pi cosine of pi times 5/6. Okay, so that would be 6 pi cosine of 5 pi over 6. Okay, so to evaluate 5 pi over 6, all right, you can draw a diagram. Okay, I know that 6 pi over 6 is the negative x-axis over here, and I have one less. So I'm up here in the second quadrant, and I know my reference angle is pi over 6. Opposite pi over 6 is going to be 1. The other leg is going to be square root of 3, but because we're moving to the left, it's going to be negative square root of 3, and this hypotenuse is 2. All right, so cosine of 5 pi over 6 would be negative square root of 3 over 2. So what we have is 6 pi times negative square root of 3 over 2, which gives us negative 3 pi square root of 3. Okay, so what does this mean? This is telling us that the velocity is negative, which in turn means we are moving to the left. So we're moving to the left. So if we're moving to the left, it depends on what side we're on. If we're on the left side, moving left, we're moving away from the origin. But if we're on the right side moving left, we'd be moving towards the origin. So now we've got to look at, okay, what's the position at 5/6, okay? So how can we do that? Well, because we have the velocity function and we have a given position, right? We can integrate the velocity function to get the remaining position, okay? So very much like what we just did, okay? So we're going to integrate, and I'm going to go from 1/6 to 5/6. Now, why am I picking those? Because I was given the position at 1/6 and I wanted to find the position at 5/6, right? So this one's the one that's given. This is the one we're trying to find. And we integrate the velocity function, so v of t dt. And I know that's going to be the position at 5/6 minus the position at 1/6, because the antiderivative of velocity is position, okay? So now I want to find this. So all I need to do is add this x of 1/6 to the other side. Okay. And that would give us x of 1/6 plus this integral from 1/6 to 5/6 v of t dt. And that's equal to the position at 5/6. All right. And you guys, there's other ways to explain it than the way I'm explaining, that, if you integrate velocity, it's the change in position, which we also call displacement. This right here, this whole thing together is called displacement. So I just want to make it clear, like there's other ways you can explain this. So you might hear other people explain it differently. That's all. It's just different. Okay. All right. So this is x of 5/6 is equal to x of 1/6 plus the integral from 1/6 to 5/6 v of t dt. All right, so x of 1/6, we got that, right? That's 2. So x of 5/6 is equal to 2 plus, all right, and then we got to integrate this, right? So this, and let's go ahead and write 1/6 to 5/6. And replace v of t with 6 pi cosine of pi t. I wish I'd done it right here. Okay. I didn't though. 6 pi cosine of pi t, right? All right. So if we let this be our u, pi t, then du would be equal to pi dt. And I forgot my dt right here. Need to write that. Okay, so this 6 can now come out. So that means I have x of 5/6 plus 2 plus 6, and then the integral from 1/6 to 5/6 of pi cosine of pi t dt. And I know this pi along with the dt, I can replace that with my du. All right, so I'm going to come off the side because I'm realizing I'm running out of room on my paper, okay, here. So this would be equivalent. So we got to keep, you know what? And I just realized I need to have an equals here. I actually wrote plus. So there should be an equals here. Okay, so 2 plus 6 times this integral, right? Which is equal to 2 plus 6 and then times, okay? And didn't mean to do that. Hold on. Because I haven't changed it to u values yet. So, all right. Okay, so 6 and then the integral, and this becomes cosine u du. And I'm showing every little step here too, okay? And then this 1/6, if I put 1/6 in for my t right here, that becomes pi over 6. And if I put 5/6 in for my t, that becomes 5 pi over 6. Because remember, I got to change these to u values. Okay. So the integral of cosine is sine. So that means x of 5/6 is equivalent to 2 plus 6. And the integral of cosine is sine. So sine of u evaluated between pi over 6 and 5 pi over 6. 5 pi over 6. Okay, so that means we have 2 plus 6 times sine of 5 pi over 6 minus cosine, not cosine. Why am I doing this? Holy cow. Sorry about that. All right. Sine of 5 pi over 6 minus sine of pi over 6. Okay. Again, 5 pi over 6, I can use this diagram up here to evaluate. Pi over 6, on the other hand, is this diagram. So I'm going to draw my second diagram up here. Pi over 6 is right here in the first quadrant. And I know the side that's opposite is going to be 1. This side is going to be square root of 3. And this is going to be 2. So sine of that's going to be 1/2. Okay. So that means x of 5 over 6 is equal to 2 plus 6 times, okay, so sine of 5 pi over 6. So sine of 5 pi over 6 would be positive 1 over 2. And then minus, and sine of pi over 6, well, that would also be 1 over 2. And so we have 1/2 minus 1/2, so that's going to be 0. So that means x of 5, 6 would have to equal 2. So now what do we know? We know our position is positive, right? So we have a positive position, and this is telling us we're on the right side. And this velocity up here says we're moving left. So if we're on the right side moving left, that would mean that we are moving towards the origin. Okay. So we could say something like this: since position and velocity have different or opposite signs. I can't remember if delta mass says opposite or if different, okay? The particle is moving towards the origin. My hand is not doing what my mouth is saying, huh? Okay, it's moving towards the origin at t equals 5/6. All right, so you're going to have to pick between these and either say different signs or opposite signs, and moving towards the origin, and then at t equals 5/6. So we got to include all of that in our rationale of why, okay? All right, let's do another example. All right, so for this next example, okay, we have a particle that's, again, moving along the x-axis for 0 less than or equal to t, less than or equal to 18, such that its velocity is given by the graph shown above. Okay, so this, what we're looking at is the velocity graph, right? So this is a graph of v of t. What is the average rate of change of the particle's position on the interval 5 to 11? Okay, so average rate of change of position. Okay, so what that is, we got to understand what that's telling us is that's the change in position over the change in time. So divided by the change in time. Okay, so for this particular problem, okay, our position is on the x-axis. So it's going to be in this interval, we're going to take, this is just slope. Okay, so it's not average value of a function, but it's going to wind up being that. So you're going to see in a minute how these are related to each other. All right. But what happens here is if we look at the average rate of change of position, that'd be x of 11, because we're doing it on this interval, minus the x position at 5 over 11 minus 5. Okay, so what is this equal to, right? What is this equal to? How can we find it? Okay, so this is what the connections that we need to make. Okay, so we could rewrite this. So this is x of 11 minus x of 5 over 11 minus 5, which is 6. Okay, so that is also could be written as 1/6 times x of 11 minus x of 5. So this right here, if you look at this, this is the change in position, right? So how in the heck can we use this graph of velocity to figure out this change in position? Well, what we can do is we can change this and realize, when do you do this? When does this happen? And it just happened earlier, right? In the prior examples, this change in position is actually the integral of velocity between 5 and 11. So we can write this as 1/6 times the integral from 5 to 11 of v of t dt. And that's how we make, okay, we can make it, because this is like we're doing a swap out, right? The substitution. This and this are identical. They're the same thing, okay? We have this 1/6 out here, right? So we're going to hang on to that. And if you think about this, right here, this is also the average velocity, okay? So the average rate of change of a position, okay, is the same as the average velocity. That's kind of weird to think about, right? But they're actually the same thing, okay? So this is going to be 1/6 times, and because this is nice geometric shapes, what we want to do is we're going to start right here at 5, right? We're going to start right here, and we want to end it at 11, so right here, okay? And we want to do this integral from 5 to 11. Well, part of this is above and part of it's below, right? And we're going from left to right, so the part that's above is going to be positive, and the part that's below, we're going to assign negative to it, okay? So then this is 1/6 times, and since this is a triangle up here, it's going to be 1/2 times the base, and we're going from 5 to 9, all right? So that's 4 times the height, which is also 4. And we're going to take care of this this triangle down here by subtracting, and it's going to be 1/2. That's going to take care of the negative part of it, and it's going to be 2 by 2. So this becomes 1/6 times, and this would be 1/2 of 16, which is 8, minus 1/2 of 4, which is 2. And so that would be 1/6 times 6, and that would just give us 1. Okay, whoops, and I just realized you can't see what I just wrote. So let me slide this up so you have a chance to write that down. Okay, and so what this is telling us is that the average rate of change is 1, okay, between t equals 5 and t equals 11. All right. All right, let's do another example. So for this next example, example 5, again, a particle is moving on the x-axis between 0 and 18, such that the velocity is given by the graph shown above. So again, this is the graph of the velocity. Find the total distance traveled by the particle during the time interval 0 to 6, okay? So we want to find from 0 to 6 right here, okay? What was the total distance traveled? Well, what we have to do to find total distance traveled is we need to use an integral, okay? And so we want to go from 0 to 6, so that's going to be the integral from 0 to 6. And basically what we want to do is take the absolute value of v of t dt. Now, this is always going to be a really difficult integral to find by hand if we had like the velocity function, okay? But what we can do is we need to realize that from 3 to 6, this graph is below. So to find the absolute value of it, well, this part, only the part that's going to be below is going to get flipped up. So really, this is going to be a graph of speed. Speed is the absolute value of velocity. So basically, this is another way of thinking about it. To get the total distance traveled, what we have to do is we have to integrate the speed from 0 to 6, okay? So right here, we're at 6, -4. That becomes the 0.64 right here. And so this part gets removed and gets reflected over the x-axis, or t-axis in this case, and we come up like this. Okay, so basically this part is gone, and we're finding this area right here, and then this area right here, and that will give us the distance traveled. If you thought of it like this too, okay, this part right here is I'm moving to the right because that area is positive. and this is the area that I'm moving to the left. This is how much I move to the left. This is how much I move to the right. Well, I don't care about left or right. I just care about moving. So that's why we make this integral positive right here, or not the integral positive, but we make the area become positive, and we just need to accumulate both of these areas to get the total distance traveled. Okay, so this winds up being 1/2 times, because this is a triangle, 1/2 3 times 4, or 4 times 3. And then plus, and then this triangle, which is also 1/2, and it's also, 3 by 4, right? Or 4 times 3. And so that gives us a total distance traveled. This would be 1/2 of 12, which is 6, plus 1/2 of 12, which is 6. So that gives us 12. That's the total distance traveled by this particle between 0 and 6. All right. So again, when we want to find total distance traveled, we have to take the absolute value of the velocity function, and anything that's below is going to get reflected over the t-axis or x-axis. Okay. So for this final example, okay, a particle moves along the x-axis with the acceleration given by a of t is equal to 6 pi cosine pi t, t greater than 0. Particle has velocity v of -6 at time 7/6. And then what we want to do here on this problem, it's different, okay? We want to find all the times at intervals 0 to 2 when the particle is moving to the right, okay? So we're given this acceleration function, right? A of t, and we're given a velocity, right, at 7/6. So this part right here, okay, is telling us that v of 7/6 is equal to -6. So at this time, at 7/6, the velocity is negative, right? Okay. Now, when is the particle moving to the right? Okay. So the particle is going to be moving to the right when our velocity is positive. Okay. So let's write this. The particle is moving to the right when v of t is greater than 0. In other words, v of t is positive, right? All right. So this is not fine. This is kind of similar to finding the velocity at a particular time, but we want to find the velocity at any time. We actually want to come up with the velocity function for this, okay? And then we got to look and see, okay, when is that velocity going to be positive? All right. So what we need to do next is we want to write an integral, all right? And we're going to want to integrate, because we're given the velocity at 7/6, we want to start our integration there. And this is what's going to be different, okay? We're not going to put an upper limit here, but we're going to put a variable, and the variable we want is t, okay? And then because this is t, we got to use a dummy variable for this t right here, okay? So we're going to, instead of using t in our acceleration function, we're going to use x. So this would be a of x dx. Now, why? X is the input for the acceleration function, and this t is going to be a different t than this one, okay? This is the t where we stop integrating at, all right? Now, because we're integrating this acceleration function, and we know the antiderivative of acceleration is velocity, this winds up being v of t, right? And there it is. That's our velocity function, minus v of 7/6. So if we add the v of 7/6 over here, we have the velocity function, okay? It's not written in a nice format that we can do things with, but it is there, okay? So if we add v of 7/6 to both sides, we wind up with v of t is equal to v of 7/6 plus this integral from 7/6 to t of a of x, and then dx. Now, what I'm going to do next is I'm going to replace a of x with 6 pi cosine pi x. All right, so this is v of t is equal to, and v of 7/6 I know is -6, and then plus this integral 7/6 to t of 6 pi cosine of pi t, not pi t, pi x, and then dx. Okay, like we've done before, and we've actually already done this one, right? We're going to let u be pi x, and then du is equal to pi dx. Okay, so this pi and the dx right here are going to be picked up by this du. So this 6 needs to come out. Okay. And so that makes v of t equal to -6 plus 6, the integral. And I'm going to, this becomes 7 pi over 6. So this is going to become a u value because I'm going to put this value right here. Okay, so 7 pi over 6. And I'm going to put, this would be pi t. And then this pi with the dx makes my du. So this becomes cosine of u and then du. All right. Now, what's the integral of cosine? Well, it's sine. So that means this is v of t is equal to -6 plus 6 times sine of u evaluated from 7 pi over 6 to pi t. So that makes v of t equal to -6 plus 6 times sine of pi t minus sine of 7 pi over 6. Okay, and then we can draw a diagram for 7 pi over 6. So 7 pi over 6 would be in this third quadrant. So our reference angle will be pi over 6. That makes this leg 1, but because we're going to go down, it's -1. And this would be square root of 3, but it would be negative, and this would be 2. And sine is our y over our r, so this is going to be -1/2. So that makes v of t equal to -6 plus 6 times sine of pi t minus -1/2, right? Okay, so that's cleaning this up for v of t. That makes v of t equal to -6 plus, and I'm going to distribute my 6 here. So this is going to be plus 6 sine of pi t. This becomes plus 1/2, but I'm going to multiply by 6. So 6 times 1/2 is plus 3. And so that makes my velocity function v of t equal to -3 plus 6 sine of pi t. Okay, so now we've got our velocity function. That is a velocity for any time value, okay? And we need that because we got to figure out, okay, we need the velocity function because we got to figure out where is this velocity going to be positive, right? Okay, now what's nice is because sine is continuous forever, right? The domain is -infinity to +infinity. We're only looking between 0 and 2, okay? So we're going to have to create a sine chart for our velocity function to see where it's positive, negative. Well, this function's never going to be undefined, but it could be 0, right? So we got to figure out, okay, where is v of t equal to 0? All right. So that's going to be, we're going to need to solve -3 plus 6 sine of pi t is equal to 0. So I'm going to add 3. So that gives us 6 sine of pi t equal 3. And then I'm going to divide by 6, which is going to make this 1/2. So sine of pi t is equal to 1/2. Okay, so we gotta figure out, okay, when is the sine ratio 1/2. So I'm going to slide this up a little bit. When is sine positive, right? Well, sine is going to be positive in the upper two quadrants, right? So it's going to happen right here. And it's also going to happen right here. Because remember, this is my y and this is my r, and r is always going to be positive. So this is the sine function is only going to be positive when y is positive. So that's going to be 1. This is going to be 1, 2, 2. This will be the square root of 3. This will be negative square root of 3 by special right triangles. The reference angle in here is pi over 6 because pi over 6 is always opposite the 1. Okay, so what are our angles here, right? So this angle, pi t, okay, it's going to have to equal pi over 6. It could also equal, if we go over here, this would be 6 pi over 6, so I'd have to back up. So 5 pi over 6. All right. And now we got to keep going till we get to 2 here, okay? Because our domain is 0 to 2 for our t value up. If you look at the very top, right up here, okay? So we got to figure out, okay, once we go past time is 2 outside, well, let's list a bunch of these. That's what I'm trying to get at. We know it's going to be positive because t is greater than 0, right? So we don't have to do negative angles. But if we go all the way to here, this right here would be 2 pi, right? But in 6, that would be 12 pi over 6, right? So we also have 13 pi over 6 for an answer. And then if we keep going, then this would be 3 pi, right? But in 6, that'd be 18 pi over 6. So that'd be 17 pi over 6. Okay, so, and then we could keep listening. If we need to do some more, we'll come back to this and get some more, okay? But what I'm going to do is to get t by itself, I'm going to multiply both sides of this by 1 over pi. So that gives me t values of 1/6, 5/6, 13/6, and 17/6, right? But what do we know about t, right? It has to be less than 2. Well, 13/6 is bigger than 2. So these aren't outside 0 to 2. So we don't even have to consider this. So here's our 2 answers. Okay, so our intervals for our sine chart is we're going to start at 0 because our domain is 0 to 2. So 0 to 1/6, and then 1/6 to 5/6, and then 5/6 to 2. Now why 2? Because that's the end of our domain, okay? And we're going to use a test point. And for this, I'd use something like t equals 1/12. Right here, a good one would be like 1/2. And here, 11/12. Okay, and then we're going to look at the sine of v of t. All right, so if we put 1/6 in here, right? If we put 1/6 in here, we would wind up in our velocity function. If we put 1/12 into our velocity function, that would wind up being sine of pi over 12, right? Which we could put in our calculator. This would come out to be negative. If we put in 1/2, this would come out to be positive. And then this one would come out to be negative. All right. And so we can tell that, again, we were looking for where the velocity is positive, right? And so the velocity is positive only between 1/6 and 5/6, right? So we would say the particle is moving right on the interval 1/6 to 5/6 because, and I'll slide my paper up a little bit, because v of t is greater than 0 on 1, 6, 2, 5, 6. It's where the velocity is positive. Okay, it's where the velocity, where the graph of the velocity is above the horizontal axis. Okay. All right, so that's just an extra example. You may come across some problems like this during your homework. Okay, and you just put, it's these weird. This is not going to give you a special right triangle or anything. So you got to put these in your calculator to determine if the velocity is negative, and you put them into this velocity function right here. Okay. All right. That's it, guys. That's it for today. This is that extra example that I had for you guys. And that's all she wrote. All right. Okay. Take care, guys.